Again, thank you very much for having me today, especially on a Sunday at lunchtime. And thank you very much to all my colleagues and the measurement definition team for helping me draft this presentation. It was a lot of material to condense into such a short presentation. So IMM, or the International Mars Ice Mapper, is really an international effort where multiple space agencies came together, all with their different main goals in terms of science and exploration of Mars, and came together to form a mission that will address one central item that is in common between all their objectives, which is the search for near-surface water ice. That is because you can imagine water ice is essential to make fuel, to provide drinking water for astronauts, for understanding the climate and geologic evolution of Mars, and many other objectives. These space agencies are in this continent: the NASA Space Agency, the Canadian Space Agency in Europe, Italy, and the Netherlands Space Agencies. And in Asia, we have JAXA, so the Japanese Space Agencies. They came together not only to form IMM as a mission, but also define the measurement definition team. In particular, the main goal of IMM is to map and characterize near-surface ice, which is the accessible ice. With these words, we mean the uppermost 10 meters of the subsurface. That's where we look for ice. This ice will provide the means for future human exploration and scientific endeavors on Mars. The MDT was assembled in order to provide payload definitions and traceability matrices to achieve reconnaissance and scientific goals to search for this ice and beyond. Also make recommendations for any supplemental payload and instruments that may be necessary to achieve the main goal, that is find ice on Mars. And also, finally, very important is to draft a concept of operation for IMM, that is how the spacecraft and the mission will operate through its lifetime to achieve its objectives. The MDT was a very large team, tens of scientists, engineers, and technical personnel from all over the world. The vast majority of us were competitively selected from our own applications. Those were available to anyone, so anyone could enter an application. And we were selected on the basis of the expertise and the knowledge that we could bring to this mission, and in particular, the search for ice. The executive committees and the leads were selected by agreement of the partner space agencies. Now, the MDT started by following guidelines and assumptions regarding the mission itself. So first of all, there is an anchor payload, a central instrument to this mission that is a synthetic aperture radar operating in L-band, which in this case means center frequency of 930 megahertz, that has polarimetric capability and also is capable of performing side-looking imagery observations as well as nadir-looking sounding observations. The orbiter that carries this instrument would arrive at Mars by 2030 and operate in a similar orbit as previous missions, such as Mars Reconnaissance Orbiter of around 300 kilometers altitude. The baseline mission timeline for this mission is 1 Martian year, or almost 2 Earth years. And mission pre-project activities provide constraints on the mission payload configurations and design for MDT consideration. And if any supplementary technologies and instruments are needed to achieve the objectives, those would need to be strictly necessary to achieve such objective while not interfering with the main payload, that is the L-band SAR. The MDT operated through a series of tasks, 3 in total. The first one being exploration-driven, and in particular, the goal was to, again, characterize and map subsurface ice within the first 10 meters in the so-called reconnaissance zone. The reconnaissance zone is visible in the image on the right and is delineated by blue lines. This region is at low to mid latitudes and low enough elevation that would allow human exploration and especially landing those locations while providing a high likelihood of finding ice. The reconnaissance objectives within this reconnaissance zone were divided among 3 different teams that inevitably overlapped in their scope, and so there was a lot of communication while we were working on these objectives. The first one revolved around ice, in particular trying to answer questions such as where is the ice and how much is there, what are its characteristics. The second team focused more on the regolith and the overburden and its properties and how to map it. And the third one instead focused on human activities and in particular characterizing potential human landing sites. The second task instead revolved around supplemental science and technologies that would be implemented on the mission. So this is in terms of what additional science can the SAR do beyond the reconnaissance objective that is finding ice. The main payload is really capable of doing all sorts of science. So we were tasked on maximizing the science return of such an instrument. And also, if there are any limitation in the primary payload, the L-band SAR, what are the technologies or additional instruments that are needed to achieve our goals, that is, find ice within the first 10 meters of the subsurface? The third task instead was focused on drafting a concept of operational FIME. So again, how the mission will operate in its first year at Mars. So regarding our findings, the very first finding was that we drafted a reconnaissance traceability matrix, which is a tool that we use to define parameters that would be observed to meet the reconnaissance objectives. And on the basis of these parameters, we defined how, like, for example, the resolution, accuracy, and methods that were how these parameters would be measured, and also if the main payload can measure it and how it will do it, and if any models are required prior to starting the mission to actually perform these measurements. Our finding was that the majority of these objectives and these parameters to be measured can be met with the primary payload. These high priority parameters, for example, are just the presence or absence of ice in the subsurface, the concentration profile of ice in the subsurface, or, for example, its lateral continuity, and many other parameters as well. The second finding was that this instrument, and especially the combination of its measurement capabilities, that is polarimetric measurements and nadir-looking and side-looking sounding and imaging capabilities, are a unique and extremely powerful tool to find ice on Mars. This has been demonstrated before, especially on Earth. For example, here on the right, you can see an image acquired by RadarSat in Tombstone National Park in Canada, where via polarimetry, they were able to identify potential ground ice that is visible in greenish yellow colors. Now, this radar actually works in C-band, so quite higher frequencies than L-band, which means that L-band, being at lower frequency, could even be more powerful in detecting deeper ice. Our third finding was that the core payload has a very high likelihood of finding the ice that is most accessible and easier to utilize by human missions. That is relatively pure ice that is covered by a thin layer of fine sediments, such as the one found by the Phoenix mission, the northern latitudes of Mars, where just with one single scoop, they were able to find relatively pure ice under just a few centimeters of sand and dust. If any other scenarios are present on Mars, so for example, rougher surfaces, thicker overburden, or larger clasts, such as boulders, and if the primary payload can't quite detect the ice there, then additional payloads such as a VHF sounder can come in and complement those observations and find the ice. In terms of supplementary payloads, the MDT identified two primary payloads that would complement the main L-band SAR capabilities. Those are a VHF sounder and a high-resolution imager. Regarding the VHF sounder, the idea is that the L-band sounder, the primary payload, is excellent at imaging the very shallow subsurface, so the first few meters at incredibly high resolution, but can't go too deep. While existing assets, and especially SHORAD, the shallow radar that is currently orbiting Mars and acquiring data, can see much deeper, but has an about 20 meters of blind zone. So to fill this gap and look for deeper ice that would be found by the L-band SAR, we thought of a VHF sounder that could really image the ice in this gap. The high-resolution imager would be similar in technology to HiRISE, so the high-resolution science experiment on Mars Reconnaissance Orbiter. So similar spatial resolution, but of course with the benefit of 15 to 20 years of technological development. And this instrument could provide corroboration for our findings in terms of subsurface stratigraphy from the L-band SAR, as well as the VHF sounder, by looking at fresh impacts exposing ice, or other steep scarps or other location that would expose the ice. And by acquiring stereo images, that is, images acquired from two different point of views, we could construct very high resolution digital elevation models that could help us further constraining the subsurface stratigraphy if it is exposed, or generate clutter simulation that would resolve any ambiguities that we see in our interpretation of subsurface sounding data. In terms of additional science, we found that the primary payload is incredibly capable and can provide a vast array of additional science capabilities that go beyond the search for ice on Mars. So starting from atmospheric science, we could look at the coupling between the surface and the atmosphere. We could do ionospheric soundings as well, for example. In terms of geological studies, we could look at polar processes and other ice-related processes that operate at mid to high latitudes, so outside the reconnaissance zone, as well as achieving a better understanding of the evolution of volcanic terrains and other landscapes that, for example, were shaped by the flow of water, and also examine unique terrains that are still enigmatic, such as the Medusa Fossa Formation that lies at the equator and is still debated whether it is a dry volcanic deposit or if it contains water ice. In terms of habitability, the radar could help locating current and recent past habitable zones on Mars where brines or ice capable of melting may exist currently on Mars. Oh, I forgot to mention that the MDT collected all these additional science operations and measurements that can be done by the primary payload, and built a science traceability matrix that describes how these science observations could be made. The next two findings revolve around the additional science and the additional reconnaissance objectives that could be met with additional payloads. So the VHF sounder and the imager not only are an excellent complement to find ice, but themselves can provide additional science to augment the scientific return of the mission. And also, IMIM could further increment its scientific output and meet all the reconnaissance objectives if it included other instruments such as instruments that are capable of measuring surface temperature, performing global measurements of winds, or, for example, obtaining a more complete measurement of surface composition. In terms of operations, the MDT found that the mission could achieve its objectives if it was operated through two different phases. The first phase will be a reconnaissance one, where the spacecraft would operate in imaging mode for at least 80% of the data returned back to Earth, and image most of the surface at a resolution of 30 meters per pixel. The remaining 20% of the data could be allocated for other focused measurements of the surface by the radar imager, or other operations such as subsurface sounding or additional payloads. After this reconnaissance phase is complete, then the rest of the Martian year would be occupied by performing detailed measurements of potential landing sites and other regions of interest that have been identified prior to the mission and during the mission along the reconnaissance phase. In terms of data returned back to Earth, MDT found that the mission can successfully complete its reconnaissance goals and objectives just with the primary payload, and would benefit again from additional instruments, but could greatly enhance its return in terms of reconnaissance and science if the mission had greater downlink capabilities. So there is a plot on the right that illustrates the baseline mode of operation. So one measurement every 4 orbits of the SAR imager in the first reconnaissance phase. And you can see that in 10 months, we can achieve 80% of coverage of the surface of Mars in this mode. But if we had a little bit more downlink capabilities and, for example, operate the instrument in only 1 every 2 orbits, we could achieve the same result in much less time, less than half of the time, and achieve a nearly complete coverage of the surface of Mars and have enough time to perform other activities as well. So our recommendation with the agency is that the agencies should explore options to augment the downlink capabilities of the spacecraft. I will conclude by leaving this link, which is a link to the final report. It's publicly available. It's 200 pages, very rich in details about the entire MDT process from its conception to the final findings. And I'll take any questions. Thank you.
I understand that it's believed that there are ice deposits as deep down as 1 kilometer or more. I would be interested, with your instruments, how deep down do you think can you detect ice or water deposits? And if it wasn't for budget limitations, are there other capabilities that exist that are not flying on this spacecraft that you would like to fly if it was affordable?
Excellent question. So it really depends on the nature of the ice itself and its overburden. So, for example, if it is covered by materials that are electrically lossy, you could have very thick ice and relatively pure ice with just a little overburden, but the radar would have a hard time seeing through it. And this would apply to any radar, not just the anchor payload, but even existing radars. And in terms of very deep water ice, the current assets, so SHORAD and MARSES, are the best bet to find that kind of ice. This mission was really conceived to find accessible ice, so ice that can be easily utilized by humans, so ice within the first 10 meters. And even then, like, try to imagine digging through just a few meters of regolith. It could be very difficult. So the focus was really the near subsurface, and that is why an L-band radar was recommended. In terms of budget, if we had, in an ideal world, if you had an unlimited budget, we could add other radar imager and other instruments that would just sense deeper. But again, the current assets are probably one of the best bets that we have in identifying very deep ice or any liquid water, really. Because mainly as you go up in frequency and the current assets are relatively low frequency, the penetration depth capabilities decrease. So we should really focus on using our current assets rather than bringing new instruments that probably couldn't really augment the scientific return too much.
Hello. Do we have idea about the salinity and concentrations of the salts in those close to surface ice deposits?
So that is actually one of the findings of the MDT in terms of models. So one of the, I'll bring up my slides. I don't know if can you see my cursor? Maybe not. But if you look at the ice presence and concentration and some other objectives that we found in our reconnaissance traceability matrix, there is one element for ice salinity.
You have a laser pointer there.
Oh, okay. It was mostly for the people online, but yeah. So there is, for example, non-ice constituents in the ice matrix. So, for example, solutes in ice or the ice matrix that would contain, for example, that would include salts. So, in part, we know what to expect in known icy deposits on Mars based on current and past observations. And if any new observations need to be made by the anchor payload and additional instruments, there are models that we found would need to be developed or further enhanced to achieve a better understanding of what kind of salts we might find in the ice.
Apologies if I missed it, but when would this mission be approved if it gets approval?
The notional indication that they gave us is that the mission would arrive at Mars before 2030. Honestly, personally, I don't know anything beyond that. We only the information we know in terms of approval of missions or budgets or anything. We know what you know. Everything is public.
So hello, very interesting study. I'm interested to read the report, but I was wondering if you could tell me what the minimum concentration of ice that you guys would be able to resolve and like the minimum difference you could resolve with the L-band radar.
Excellent question. That again depends on the ice, the characteristics of the ice itself, how deep it is, and how much and what kind of regolith is on top of it. So if the right condition exists, especially the polarimetry capability of the SAR in imaging mode could really identify even very small concentration of ice. This has been demonstrated, for example, on the moon for the polar deposits from ground radar observations, where they found ice concentrations that were then later revealed, for example, by the L-Cross mission to be apparently relatively small. Now, I don't remember the numbers, but if the right conditions exist, the ice concentration could be relatively low and would still be identified by polarization.
Thank you. I have a follow-up question on the timing and decisions on moving forward. I understand there was a budget proposal this fiscal year for NASA to pull out of this project. Where are we on that decision? How would that affect the timeline? We have the slogan "Humans to Mars" this decade. It'd be great to get the ice mapper out there before the humans arrive.
That is an excellent question, but I don't know anything anything beyond what you already know. We were not given any information about budgets or upper level decisions on these missions. We were only tasked to define measurements that this mission would make. We don't know anything else.
The high-rise results were publicly posted on the internet. Will the data from this be available in the same kind of worldwide fashion?
That depends on what the partner agencies will decide with this mission. This was not something that was tasked to the MDT. So the answer is I don't know. It really depends what the partner agencies eventually decide for the mission. Thank you.